and balance our reaction.
Sodium and nitrate both have what charges? 1, right? Positive 1 and minus 1. Magnesium and carbonate are both in what, have what charge? 2s. Okay, so that means they'll fit together fine. MgCO3. Okay, it would yield a combination now of sodium and carbonate, which would give us Na2CO3 plus Mg parentheses NO3 2. Okay, are we on the same page with those compounds? All right, and then to balance our reaction, we would need 2 sodium nitrates. Okay, hopefully that part is no problem so far, right? All right, so let's say that we start now with 28 grams of sodium nitrate and 36 grams of magnesium carbonate. And we want to find out what the limiting reactant will be. Okay, can somebody explain to me in kind of simple terms what a limiting reactant means? Raise your hand and see if you can explain to me. Yeah, Jenna, what do you think?
It's how of the reactant that limits like what you can make. So once you run out of that, you can't make any more of the substance.
Exactly. It's what's going to run out first in our chemical reaction. Okay, so we're saying if we dump both of these amounts in here, our chemical reaction will produce sodium carbonate and magnesium nitrate until we run out of something, right? It's kind of like an assembly line. You're packing boxes, and once you run out of one of those items, right, you can't make any more of those boxes, or you can't make any more of that item, okay? So in the video, I think it talked about making like hamburgers or cheeseburgers or something, right? We had so many patties that had to go into it, cheese and buns and whatever. And so you run out of one substance, you can't make any more of that product. It works the exact same way with our limiting reactant problems here. Okay, so when we see 2 starting amounts, right, we have a starting amount of sodium nitrate and a starting amount of magnesium carbonate, what do we have to do there? Yeah, we have to do it twice, right? We do the T-chart 2 times, 1 with each starting amount. Okay, does it matter to us which of our products we go to? No, but what has to be true? Exactly, you got to do the same one, okay? And in this problem, since we're just trying to find the limiting reactant, do we have to go all the way to grams, or could we stop at moles? I didn't really talk about that in the video, but I want you to understand this. If I'm going to sodium carbonate, and I want to compare how much of that product can be formed, I can go all the way to grams on both, right? Or I could stop at moles on both, because the amount, the ratio would be the same, right? If I have 0.5 moles and 1 mole, it would just be, half the amount of grams to the total amount of grams, right? Does that kind of make sense or not so much, right? Going to grams all the time will always work. Sometimes you have the ability to stop at moles of each of those products, okay? So let's go ahead and try one here. We're just going to find the limiting reactant. That's our only goal right now, okay? Find the limiting reactant. So we want to do both of those T-charts. So let's say we start with 28 grams of sodium nitrate. And which product would you like to go to? Which sodium carbonate or magnesium nitrate? Does it matter? It makes no difference when we go to. Half the class could go to one, half the class could go to the other. You're still going to get the same limiting reactant, right? You wouldn't get the same amount of the product, but you still get the same limiting reactant. Okay?
This is both for the same for each one.
You have to use the same product for each of these T-charts. That's right. Okay, so we'd go grams of sodium nitrate to 1 mole.
To put it into?
We can either go to moles of sodium carbonate or grams of sodium carbonate. We don't even have to go to grams here, since it's not asking us like how many grams. All we're doing right now is finding the limiting reactant. So we're going to go ahead and stop at moles.
Does it matter which one we go to for both one?
No, it makes no difference. You just have to do the same one both times. Yeah. Okay, and our mole ratio here is 1 to 2. Okay, molar mass of sodium nitrate would be 85, okay. Do we agree there on our amount of moles? Okay. Now, since we have our other starting amount, we need to do our T-chart again. And our molar mass here was about 83. So what we got for molar mass, or not so much? 84.3. You're right. You're right. I used the wrong one. 84.3. Yeah, I would. With that Wait, what do you mean? Yeah, with magnesium, I wouldn't round that to 24. If it's that decimal is kind of in the middle there, I'd keep that. Yeah. Okay, so 36 divided by 84.3. We get 0.427 moles. Okay? And what I'm saying here is in our last video, we went all the way to grams, which means we would take each of these mole values times its molar mass, and we'd get the number of grams. Right? To finish that T-chart, to go all the way to grams, we would take this times the molar mass of sodium carbonate, and we take this times the molar mass of sodium carbonate. Right? We're multiplying both of those by the same thing, so we're looking at the same ratio here. Okay? So which of those is our smaller amount of product that is formed? The top. So that means we go back to the beginning of our T-chart and we say sodium nitrate would be our limiting reactant, right? It's going to run out first. Does it always work that the smaller amount of starting reactant, is that always going to be the limiting reactant? No. Okay, that's not always the case. So don't just think like, oh, we're starting with less of this compound, so it's going to run out first. That's not always the case, right? It has to do with the mole ratio, and it has to do with the molar mass. Okay? All right, so we know that we could form 0.165 moles of our product. Okay, now I want to take this one step further, and we want to find out, since sodium nitrate was our limiting reactant, it's going to run out first. We want to find out how much of magnesium carbonate is left over. We can't just subtract, because right now we're comparing the amounts of product, and we're starting with grams of our reactants, right? We can't compare grams to grams because they have different molar masses, because they have different molar ratios. Okay, do we understand the goal of what we're doing here? We want to find out how much of our excess reactant there is. Okay, what does excess mean? Extra, leftover, more, very good. Okay, does that make sense what our goal is here? Okay, we want to find out. So in order to do that, we have to compare those two items. Okay, so that means we do yet another T-chart. Okay, but we're going to compare this limiting reactant, and we're going to see how much of this reactant is used during that. Okay, so let's start a different T-chart here. Sorry, I know these problems are going to take a lot of room. Okay.
That's why we're going to have a couple on our test, right?
Something like that. I'm telling you, you're going to have to be able to build one and balance it from the ground up then do a limiting reactant, and then find percent yield. Like, you're going to have to do one problem that puts everything together, so just
So if you
prepare
screw up-
yourself.
So if you screw up on the very beginning, then you're just screwed.
Well, that wouldn't be good, no.
Depending
All
on
right.
how to do it.
You gave me a little bit of hope, saying, well, that, and then you're like, no, it's not.
Okay, so now we want to see if we use all 28 grams of this sodium nitrate, how many grams of our other reactant of magnesium carbonate are going to be used. Okay, that's what's coming out of this T-chart now. So we're going to go from grams of sodium nitrate, and we're going to do a T-chart to grams of magnesium carbonate. That would tell us how many grams are used during that reaction. Okay, and then we'll be able to look at the final and the initial of that magnesium carbonate. Okay, so since we started with grams of magnesium carbonate, we need to go 2 grams of magnesium carbonate so that we can compare them pretty easily. Okay, are we on the same page there?
Yeah.
Kind of. I know this seems a little bit abstract still. Okay, so let's go from grams of sodium nitrate to grams of magnesium carbonate. We're comparing now how much of this other reactant was used up so that we can calculate how much is left over. Luckily, we already calculated molar mass. Okay, so what did we get for our amount of magnesium carbonate that was used during this reaction? Good. 13.88 grams. Okay, so is this our leftover right here? This tells us how much was used, right? This tells us if we put in 28 grams and we run our chemical reaction according to our molar mass, right? We need 2 moles of sodium nitrate, so we need 1 mole of magnesium carbonate. According to this calculation, if we use all 28 grams, that means that 13.88 grams of magnesium carbonate would be being used. Okay, so in order to find our leftover, what should we do? Yeah, subtract that out of the 36. So we would take our starting amount right here, 36 grams, minus 13.88, and that gives us 22.1 grams left over. Yeah. Because when we do our T-chart here, we're saying if we use all 28 grams of sodium nitrate, which we know it's going to use it up because it's the limiting reactant, once we use all 28 of that, we would only use 13.88 grams of our reactant, okay, our second reactant. So in order to find out how much is left over, we're going to take the starting amount of magnesium carbonate, right? We put in 36 grams. We used up 13.88. So in order to find out how much is left over, we subtract what we started with from what we used. No, what we started with minus what we used. Okay? And we got about 22.1. How does that feel? Okay, so I balanced the equation for you. To find our limiting reactant, first thing we want to do is start with what we know. It doesn't matter which of those you do first. You could start with 53 for, as long as you do both. It makes no difference which one you do first. I would end up going to grams because we have a percent yield, and that deals with grams over grams. Yeah. You could theoretically, since you don't know what the final question's going to be, but I'm going to tell you, go ahead and go to grams. Yeah. So our overall goal here is going to be to find the actual yield, just a heads up. So you should go all the way to grams. Bless you. Based on those projections, based on those theoretical yields, which would be our limiting reactant? K3PO4, right? When we ask which the limiting reactant is, we don't circle this and say this is the limiting reactant. Like, no. Right? That's not telling us that's a limiting reactant. We looked, which gives us a smaller product. Then we go back and we say this compound would give us a smaller amount of product, which would then be our limiting reactant. Okay, so our limiting reactant here. No, we say limiting reactant is K3PO4. We tell the compound itself, right? The limiting reactant is a compound. It's not the starting amount. Good question. Okay, so the limiting reactant is K3PO4. Okay. So we said that we yielded an 85% yield on this reaction, and our goal was to find what the actual yield was. We took our theoretical yield, which came from our T-chart, of our limiting reactant, right? This means theoretically this is the maximum amount of that product that can be formed, right? Potassium phosphate will limit the reaction to only making that much. We would then plug that into our percent yield equation, actual over theoretical. We multiply those two things together, and we get about 55.8 grams of potassium nitrate that actually is yielded from that reaction.